Hello, in this mini lecture I will introduce a full adder standard device, full adder. And full adder adds 3 bits together. So 3 numbers of 1 bit each, which are denoted as ABC. So the maximum value is 1 plus 1 plus 1, which is 3. So we need 2 bits to get the proper result in all possibilities. The more significant bit, this one, will be called or is called Cout. It is the same letter as literal C, but with underscore and out. So it is a standard name, and the name of lower bit is S, sum or S only, okay? And full adder, it is name as FA in the abbreviation of it. And how is it important? How is it important? 3 bits together? Why not 2? Why not more than 3 or less than 3? Okay, of course, it results from the addition using pencil and paper method. Let's suppose we'd like to add 2 numbers, 10111 and 10011 together. Arithmetically, please consider this. Look at this. This is a symbol used in logical addition. In this context, it means arithmetic addition. So if we add it using using paper and pencil method, we add 2 bits together first, and 1 plus 1 gives you 0, which is 2, okay? And the lower bit is put here, and the higher bit is put here to be added to the next position, to the next, together with the consecutive bits of the 2 numbers A and B. Okay, let's denote A and let's denote B. This is a A1 and B1 bit, and we must also add C out. Okay, and that's why we need a full adder, which adds 3 bits together, to construct the system which can add numbers of n length, okay? Because we repeat this procedure many times to get the overall result. So now it is 3, lower bit is 1, and the higher is 1. 1 plus 1 plus 0 gives you 2 again. So the lower bit is 0, and the higher is 1. 1 plus 1, 0 plus 0 is 1, and 1 plus 1 is 0, and 1, it is a carry bit. So the result of adding arithmetically A and B is 10, 10, 10, okay? So in order to design such adder, which can add numbers of arbitrary bits, we must construct first the full adder cell. We can add 3 bits, okay? A, I, B, I, and carry. So this is this one. Truth table for this is quite simple. Cout is a higher bit than the sum. Let's denote it as S only. 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. All possibilities of ABC. Sorry. All zeros gives you 0. 0 plus 1 gives you 1. The same result is here, 1. 2. 1. 0 plus 1, 1 plus 0 plus gives you 2. 1, 0. 1, 1, 0 gives you 2. And the last row gives you 1, 1, which is 3. Okay. Now we must minimize the function to get the overall, to get the system. AB, let's say, will be in columns and C in rows. Gray code, as you remember, hope. Okay, and you've got the kernel map. And let's put zeros first, and the remaining cells will be ones. So all zeros gives you zeros, ABC001 gives you 0, 0100, 0, and 100. It's here. The remaining bits are ones. Okay, and in order to minimize it, you've got the cout. It is a K map for cout. Cout is equal to. From this group, the result is BC. So BC plus. From this row, you've got AC. And from the horizontal, from the vertical one, you've got the AB. So it is a minimized sum of product form of cout. Okay. What about S? We can construct, of course, we must construct a similar K-map for S. Let's do this. So as before, AB will be in columns, C in rows, and gray code 10. All right. And look, let's fill in with zeros first. So all zeros give you 0, 0, 1, 1 gives you 0, 0, 1, 1 is here, 0, 1, 0, 1, 1, 0, 1 gives you 0, and 1, 1, 1, 0 gives you 0, 1, 1, 1, 1. And look at this table, you don't have any neighbors, okay? This is a single one, no neighbors at all. So you cannot minimize it. You simply must construct or find express as a sum of these meters. Okay, so full products. So not A, not B times C. It is this one plus. Not AB times not C plus this one is ABC plus this one is A not B not C, A not B not C. What can we do next? Of course, if you have only AND or NOT gates, this is the lowest cost solution. But if we have XOR or XNOR gates, we can go further and minimize the function manually. Look at this. Not B, not C, ABC. Let's have a look here. A is a common factor here, and not A is the common factor here. So try to factor out it. And inside the parentheses, you've got the not BC plus B not C. And similarly, A, BC plus not BC. And as you remember, I hope you remember that this expression is an XOR expression. And this one is an XNOR expression for B and C. So now you can express it as not A, B XOR C plus A, B XNOR C. And for two variables, you know that this is inverted XOR. So now you can express it as not A, B XOR C plus A, B XOR C inverted. And then you can see that this one is a, let's say X. This one is not X. Okay, I can denote it in this way. So now you've got something like this. S is equal to not AX plus A and X, which is XOR of A and X, as here. Yeah, it's the same expression for A and X as before. So it is equal to A XOR X. But because X is simply XOR of B and C, you can then express it in A XOR B XOR C. Very simple compared to this. Okay, it requires only 2 XOR gates. Let's have a look in implementation, realization of the full adder cell. It is I will recall Cout as you remember. It is AB plus BC plus AC. Okay. And S is A XOR B XOR C. And please memorize these two equations. They are very important. Okay, memorize it. You must know it by heart. So now you can construct the system using gates and draw the diagram. And the first gate and the second gate gives you S. Okay, A, B, and C. And then you've got what? You've got AB, BC, and AC, and the outputs must be added together using OR gate to get C out, and here you've got S. So let's connect the appropriate bits A and A, C and C, and B here, and B here. So the cost factor is how many inputs are there in the system? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there's a 13. How many gates? 1, 2, 3, 4, 5, 6. 13, 6 is the cost factor of full adder cell. And what else? You can construct adder containing n-bit arguments, n-bit adder, using full adder cells. Okay, FA. Let's have a look. It is a full adder. We have developed. Alright, and just developed. You've got 3 inputs, ABC, and then the output, which was called Cout, is connected to the next full adder cell. We connect the next bits, and so on, and you've got the nth minus 1, so A n minus 1 and B n minus 1 bits, okay, which and C n minus 1 is here. FA, the same cell containing the gates I just presented, and the overall result of the sum, it is here. S is equal to A plus B. It is arithmetical addition. Okay, it is A n A0 B0 bit and A1 B1 bit, and here is a C0 which must be equal to 0. So we connect this to the ground. Let's for example, in the correct. And now you've got So it is an example of a so-called iterative circuit. There are many examples in the real world where you can find the system to be implemented in this way. So 1-bit cell connected to another 1-bit cell, etc., giving or resulting in n-bit function or n-bit system. Thank you.